let's talk about sets of points in space. Better said, let's talk about sets of points in space determined by equations and inequalities. So that conversation will happen over here. Before we get started, I want to talk about examples of sets of points in the plane and on a number line, just to give us a little intuition or remind ourselves of things we knew going into this. So let's say I have a number line, and I want to talk about all the points where x is equal to 3. Well, that's going to be very boring. It's just that point right there. And so maybe we expand our ideas here, and I say I want to find all the spots where x squared is equal to 9. And well, at least that's a little more interesting. That's 3 and minus 3, so I get 2 points. And then finally, maybe I say something like x is greater than 3. And then on my number line, I'd have to indicate that I was shading all the points to the right of 3, but not 3 itself. All right, so on the number line, sets of points, something like that. So now let's think about examples in the plane. So let's think about the equation y equals 3. Well, those are all the ordered pairs in the plane where y is 3. Doesn't matter what x is, as long as y is 3, and so we get a horizontal line. And then maybe someone came along and said, let's talk about all the points where x is equal to 3. Well, wouldn't matter what y is as long as x was 3, and we'd get that nice happy vertical line. And then maybe while we're in the plane, someone said, how about all the places where x squared plus y squared is equal to 9? And we'd say, hey, well, that's the equation of a circle of radius 3 centered at the origin. And maybe we should do an inequality. Let's say we wanted to look for all the points where y was bigger than or equal to x. Well, the line y equals x would look like this. I'm looking for all the ordered pairs where the y is greater than the x. Well, that solid blue line are all the points where y is equal to x. And so these points shaded above would be the points where y is larger than x. All right, well, that got a little messy, but examples of sets of points in the plane, let's look at examples in space. Let's think about the equation y equals 3. What points in space would I be talking about then? Well, not too dissimilarly, right? I know y is 3. In the plane when y is equal to 3, I get this purple line because it didn't matter what x was. Well, now I'm in space, and I know that y is equal to 3. And so I could think about that line that would be in the xy plane. And that would be all the spots where y is equal to 3 and x didn't matter what it was, but z is definitely 0 in the xy plane. And so what I realize now is x and y get to vary. So instead of getting just this line, I get a plane. All right, I get all those nice happy points above and below that line, perpendicular to the y-axis, crossing through at y equals 3. And so a little bit hard to draw, but if I think about an x and a y-axis and a z-axis like this, at y equals 3, I'd get a plane that cuts through. And so if I wanted to write down what happened there, this is the plane parallel to well, I look at that, that's the x-axis, and the z-axis is parallel to the xz plane. Crossing the y-axis at the point 0, 3, 0. And there's any number of ways we could describe this plane. It's also the plane that's perpendicular to the y-axis intersecting at that point. All right, let's think now about the equation x equals 3. Well, we can use the same logic to decide that that would be the plane parallel this time to the YZ plane hitting the x-axis 3 units out. And so we could try to draw that in there using the same kind of strategy. X is always 3, but Y and Z get to be whatever they want, giving me that two-dimensional plane that sits parallel to the YZ plane. Okay, well, continuing in R3, let's think about the equation Z equals 3. Well, that would be the plane that's perpendicular to the XY plane, 3 units above the XY plane. X and Y get to be whatever they want, but Z is always 3. I get that nice happy plane. What's nice about this example is it's a lot like the last two, except for I could imagine drawing an x-axis and a y-axis on the board and then letting the z-axis and our right-hand coordinate system come right at the camera, and then that plane at z equals 3 would simply be a plane parallel to the board, 3 units above the board between the board and the camera. Right? That would be the plane z equals 3. All right, well, maybe let's look at an inequality. Z is bigger than or equal to 0. Well, the xy plane itself is all the points where z equals 0. Z's that are bigger than 0 are simply the ones above it. And so we could think about this as the upper half of space, including the xy plane. I did a very poor job of drawing it there, but in this three-dimensional coordinate system, z bigger than or equals 0 are all the points in the board and above the board, even past the camera. Well, I just put my hands moving up towards the camera and then above the camera, which you can't see clearly because that's how above cameras work, but I think you get the idea. All right, and then one more example for this video. Or actually 2 more examples for this video. I want to look at the set of points described by this system of equations and inequalities. So z is equal to 2, x is less than or equal to 0, and y has to be bigger than or equal to 0. And so I have my right-handed coordinate system to think about. And what I want to think about now is what these things are telling me. Well, z equals 2. I can think about that as a plane that's 2 units above the xy plane, parallel to the xy plane. So what I've done there is I've sketched out what I'm going to be to think about like axes, but are in that plane, they're 2 units above. All right, x is less than or equal to 0 and y is bigger than or equal to 0. We'll have x-axis and y-axis. The x's that are less than or equal to 0 are back here. The y's that are bigger than or equal to 0 are here. And so in this plane that's 2 units above the x-axis, I'm talking about this quadrant in that particular plane, where x is less than or equal to 0 and where y is bigger than or equal to 0. And if we were thinking about the xy plane, this would be the first quadrant, and so this is the region in the plane z equals 2 above the second quadrant. Okay, and then one final example of equations and inequalities determining regions in space. I want to consider x squared over 25 plus y squared over 16 is equal to 1, but only when z is equal to 3. All right, if we were in the classroom together right now, I would stop what I was doing and ask everyone to just pretend they were in the plane for a moment and tell me what that is the equation of. So think to yourself, what is that the equation of? All right, I'm hoping out there some of you said the word ellipse, because this is the equation, in the plane at least, of an ellipse. And so x squared over 25 plus y squared over 16, a is 5, b is 4, and so if I was just graphing this in the plane, I hope I would do a nicer job than this, but I graph a nice happy ellipse with a major axis that was 10 units long and a minor axis that was 8 units long. But now what I realize is that's in the xy plane. That would be when z is equal to 0 in my right-handed coordinate system. Now I need to draw that when z is equal to 3. So I'd get that same ellipse, but just up 3 units. So again, I'm in a plane 3 units above the xy axis. Axes. And now I just need to draw an ellipse, thinking about x, y, and z. All right, in the x direction, I need to go out 5 in both directions. In the y direction, I need to go out 4. And then I can sketch in my ellipse. Well, I've drawn better ellipses. I've probably drawn worse ellipses, but as long as we all agree that it's an ellipse that's shifted 3 units of parallel, 3 units up and parallel to the xy plane.